Okay, so I guess let's get started by talking about kind of the trichotomy within analytics. So you can think of three different kinds of analytics. Descriptive analytics, and that kind of answers the question, what happened? So, and in Tableau is mostly about descriptive analytics. They do things like sum and average, which aggregate and describe data distributions. In contrast, predictive analytics asks the question, what will happen? So in Tableau today, our forecasting feature, our trend lines feature, these are examples of predictive analytics. And then finally, there's prescriptive analytics, which is how can we make things happen? And this has to do with kind of causal analyses, what would happen if I did this instead, and that kind of question. And as you can see, as you kind of climb up the ladder, you start extracting more value out of the answers provided by these mathematical models, but it also becomes increasingly difficult to get the math right. All right, so this is an analytics trichotomy. But there's also kind of a trichotomy within machine learning that has intriguing parallels with this. So you may have heard the distinction between unsupervised, supervised, and reinforcement learning before. So unsupervised learning takes as its input an array of data, which we'll call X, and descriptive analytics outputs a summary, for example, an average or something more complex. In contrast, supervised learning, in addition to the data, it also takes on labels that we'll call Y-train, and it outputs predictions, kind of new instances of these labels. All right. Finally, reinforcement learning, in addition to accepting data, it also accepts a reward function, which we'll call R, and it outputs an action, A. So there are intriguing parallels between these, but what I want to do next is talk about what's wrong with supervised learning. So in supervised learning, in computer vision, on the left we have the training data, right? So we have millions of these examples of images that we feed to our algorithm. And these images that we feed to our algorithm must have these labels, in this case, yellow bounding boxes that describe where the vehicles are in this image. And if you give enough of these images, enough of these ground truth labels to our algorithm, it's able to take an image that's unlabeled, say this image, for example, and it now knows enough to generate its own bounding boxes. And this is what supervised learning is. But if you go back to the original image, this is not a biologically plausible account of what your retina actually receives. At no point do your physical eyes receive this bounding box information. And there is really no other way that you as a human being can receive this information before you learn how to do it yourself. So we need to make, so it's one of the most prominent intuitions is that supervised learning isn't good enough, that we need to make our algorithms less reliant on these ground truth labels. In a sense, these labels are cheating. All right, so we might be concerned that perhaps reward signals are artificial in the same sense. Can we make the case that our brains receive reward signals? One physical model of the reward signal says that you can, in the loop notation that I introduced in my brain talk, we move from world perception, which acquires our data via sensors and outputs actions, and we could model reward as physical. So for example, if you stumble onto a water source and you're thirsty, you could say that the water is objectively rewarding, and that's perhaps what's going on with the reward signal. But I think that when I presented my two loops hypothesis, that the hot loop, which perceives and regulates the body, sheds light on reward. So specifically, I'm going to be presenting the hypothesis that reward is derived from body status, that water is not objectively rewarding, but the ability of water to quench our thirst, that is what generates the reward signal. Okay, questions before I move on to the math, I guess. All right, cool. So it's philosophical relation to machine learning. Now let's, so what I wanted to do is I wanted to kind of describe the math of reinforcement learning. And this should objectively be presented over the course of maybe 4 or 5 weeks. That said, since I only have 45 minutes to present it, I'm going to condense kind of the essence of the math to you in hopefully a way that's memorable and give you a foothold if you decide to pursue reinforcement learning later. So the very base of the foundation of reinforcement learning is Markov chains, and we'll turn to that now. So let's imagine that we're looking at weather data. So imagine a situation where the probability that any given day is sunny is 50%. So on the average, as the days fly by, we might expect kind of a distribution of weather that looks like this, kind of a, yeah. All right. But what if weather events, so we might suspect that the above account isn't accurate enough. But so what if the probability of sunny is still 50%, but the transitions are a bit stickier? So what if we wanted to model weather to look something like this, where you have a lot of rainy days in a row, followed by a lot of sunny days in a row? All right, to model a stickier transition function, we need to account for our knowledge of the present state. So specifically, what we'll do is, instead of modeling just the probability of sunny, we'll model the probability that it's sunny given that the previous day was also sunny. So in this case, if it's sunny today, it will be sunny tomorrow at 90%, and if it's rainy yesterday, it'll change to be sunny today at 1%. And this encodes kind of the intuition that weather doesn't tend to change day by day. And conversely, we can also say that maybe it's rainy. We can say this. Okay. So this is one way to make our model more complex, but we can make it increasingly complex. We can model increasingly interesting phenomena by extending, by conditioning on more and more of the past. So we could instead say, okay, maybe we care about yesterday and the day before. Maybe that will help us improve our predictions of tomorrow's weather. All right, so the Markov assumption, that's the basis of Markov chains, is that if we can forget this stuff on the right, and we can say, if we understand the present, we can forget the past. So one way to think about this is in terms of physics. So if you have a description of, say, particles, and you know kind of the particle's location, that's not enough to predict where the particles will be tomorrow. But if you expand the amount of state knowledge that you have, so if you not only know the position but also the velocity of particles or bowling balls, then you are able to predict tomorrow just based on your knowledge of the present. So that's kind of a physics intuition for why the Markov assumption might be a reasonable thing to do. Questions before I move on? Okay. Oh yeah, and okay, so we have this kind of 2x2 quadrant here. One of the cute ways that Markov chains visualizes this is with kind of a graph that looks like this. So each vertex on this graph represents a state, rainy or sunny, and each arrow or edge, directed edge, represents the transition probability. All right, so another example quickly to kind of solidify this way of modeling things. So let's suppose that you have a data set that, that captures loan classifications. So there's 4 possible categories of loan. You can label a loan as paid in full, good standing, behind schedule, or in collections. So you translate each of these 4 classifications into a vertex. And then you inspect your data table and you discover the following facts. So accounts that are in good standing, loans that are in good standing, 10% of them eventually transition to being paid in full. 10% eventually transition to being behind on payments, and 80% remain in good standing. And we represent that graphically like this. And then by further inspection of our database, we can also discover the following facts. Bad loans, 10% are paid in full, 40% return to good standing, they catch up on their payments, and 10% are sent to collection. And, we can update our graph to look like this. Okay, so in this graph, you'll notice that F and C, paid in full and collections, are terminal states. Once you reach them, you can't escape, if you will. And that's by design. That's just how our database is constructed. So once we construct this graph of all of our probabilities, we can answer the following questions. We can answer, what's the distribution of loans? How many loans go into paid in full versus collections? And we can also answer individual questions. Some person has a loan in good standing. How likely is that person to have that loan be paid in full? All right. So that's a Markov chain. So how you answer questions mathematically in Markov chains. So let's imagine that we have the following simple Markov chain on the top with these transition probabilities, and we're asked the following. We know that this original state is A, and we need to compute the state at time t for this person. So the way we do it is we take this graph and we unweave it. So A transitions to, at T1, there's a 20% chance that it's in A, and an 80% chance that it's in B. And then we unweave it again. We say, okay, at time 2, if we're in B, then there's a 20%, 60%, 80%. But if we're in A, we also have to account for that. And if we're in time 3, we also have to unweave as follows. So, so you can imagine that as you progress in time, your model needs to account for an increasingly large tree-like structure. But now that we've unweaved the Markov chain, we can answer questions from it. So let me introduce the actual mathematical notation for one slide, and then we'll forget we saw anything. So to compute, so let's say we are presented with the following question. Person A has a loan of status, person X has a loan in status A at time 0. What is the likelihood that that loan will be classified as C at time 3? To answer that question, what we need to do is we need to take the sum of the paths over the product of the edges of each transition probability. So let me unpack what that means. So to answer S3 of C, we need to take the sum of all possible histories of P of C. So there are 3 ways in which a person can have a loan of class C at time 3. There's the top, the middle, and the bottom. So for each of these 3 histories, we need to find the path. We need to multiply by the path. So the first one, the top one, we need to model P C given B. So that's this line right here. And you'll see that on the graph, this blue edge is probability 0.8. And we need to keep multiplying by the rest of the history. So to get from A to B, that's 0.8. To get from A to A, that's 0.2. And the probability of A, we know, is 1. So that's how you compute the probability of one path to C. Similarly, for the other 3 paths, you do the exact same thing. You just multiply each of the weights of the edges together, and then you sum over all 3 paths. And the final number is 89.6%. So if a person starts off in state A, by the time 3 days have elapsed, then there's an 90% chance that they will have arrived in state C 3 days later. So that's how you kind of extract a mathematical answer out of the Markov chain. Questions before I move on? Apologies if this is too complex or too simple. All right. Okay, so now we kind of worked through a graphical model. There's actually a way to do this that's a lot simpler. So the idea is you need to take a Markov chain, and you need to, rather than working with this graphical model, you can recast it into the language of linear algebra. So let's think about a transition matrix. That's on the rows, that's the states that it's going from, and the columns, that's the states that it's going to. So the top row, this encodes the following information, that A to A is 0.2, that's this arrow right here, 0.8, and there is no way to get from A to C directly. And similarly, you can construct the rest of the matrix by this logic. So 0.1 is these two forms are completely interchangeable. You can reason with Markov chains, and you can reason with transition matrices. So why would you want to reason with, why are transition matrices easier? Okay, so we've seen previously that functions take inputs and they spit out outputs. So they can take, functions can take vectors and spit out output vectors. So if you have a transition matrix, that transition matrix can input a state, accept a state as input, and spit out the output state. So that's what this transition matrix is going to do for us. Is let's imagine that we have an input state that there's a 100% chance that we're in A at time 0. Now we're just going to throw that this vector into our transition function and learn the distribution over time. So this is our initial state. We're going to multiply, use matrix multiplication to multiply S0 times T, and that'll give us S1. Matrix multiplication again to get us S2. Matrix multiplication again to get us S3. This is fairly straightforward, but what I want to point out is that this number right here, this 896, we learned that extremely easily, but that's the exact same number that we arrived at very laboriously on this slide. So this illustrates that linear algebra makes our mathematical lives a lot simpler. Okay. And with that, I'm done with Markov chains.
Did you have to do this in the loop then? You did have to do form multiplication?
Yeah. Yeah. And there is a way, if you read up on eigen decomposition, eigenvectors, eigenvalues, there are ways to jump to the correct time step without going through this.
So does this require like these?
Yes, yes. Very good. Yeah, it does. Yeah, so if your state, you have 3 states, this is fairly trivial. But if you have n states where n is 10,000 pixels, this computation becomes much less pleasant.
So I have a question. Can you hear me?
Yeah. Yeah, I can hear you.
Just to make sure, I think it's possible to just multiply the matrix or power it appropriately first, and then multiply it by initial state. We should get the same result, or?
Oh yeah. So you're doing what's called, I believe it's called a power. Taking a matrix to a power, which is
yes.
Arbitrarily many times. If you decompose it into your eigenvectors and your eigenvalues, what you can do is you can take your eigenvalue matrix and you can raise each eigenvalue to that power, and that's the same, and that's the matrix that you multiply with. I'll send out a link if you guys.
Yeah, because the current procedure was to do each step separately. Whereas, for example, if you can power the matrix, you can do that faster, right?
Yes. Yeah. Exactly.
And then you can multiply the result by the initial vector. So.
Yeah. Yeah, that's exactly right. And you can use this kind of power trick to approximate what happens at S of infinity. So what's the distribution? Yeah.
Okay. Thanks.
Yeah. All right, fair enough. So yeah, math, it's fun. Okay, so let's talk about Markov decision processes. So we saw that Markov chains are kind of have 2 things. They have a set of states and a transition model. Markov decision processes extend Markov chains by adding 3 new elements. We have states and transition models, but we also have actions, a reward function, and a temporal discount factor. And I'll be explaining each of these in the following 3 slides. So MDPs are Markov chains that are a little bit fancier. That's all they are. I also wanted to mention that you can also extend Markov chains differently to arrive at hidden Markov models by adding a Y term. And you can also add an assumption about the graphical structure to arrive at a graphical model called the MRF. Okay, so Markov chains are kind of the basis of many different formalisms. Markov decision processes are just the one that's most relevant to reinforcement learning. Okay. Okay, so yeah, let's learn what am I talking about when I talk about actions, rewards, and discount factors. Okay, so this is grid world. Grid world, we'll call it. And in grid world, we have a set of states, and we can represent this as maybe just a grid with a Pac-Man-like grid. Grid world has rewards that are associated with states. So at these 2 locations, we have a positive and negative reward. And elsewhere, we have no reward at all. Okay. Actions represents things we can do. So in grid world, we have actions where we can move in any direction. And a transition model is the probability that we arrive at tomorrow's state, given today's state in an action. So we can imagine a perfect robot that if it chooses to go somewhere, it does go somewhere. But we can just as easily account for noise in the robotics. For example, if a robot chooses to go north, perhaps it malfunctions and 10% of the time goes west or east. So that's a transition model. Okay, so and now we have a concept of a policy. So
the
transition model is it's generally taken to be the same at every location, although it can vary. So it's basically it's this probability distribution where you can have it be the same at every SFT, or you can have it vary based on the location to maybe account for how bumpy the terrain is. So it really depends to you. Depends on your design choices. I did also want to mention the transition model. You can assume what it is a priori. But reinforcement learning, one of its claims to fame is you can learn the darn thing online. So, yeah. All right, cool. Policy as a state action pair. So let's imagine. So what the robot wants to learn is it wants to learn what action should I take at every state. So in grid world, we can imagine that if I land in this state, in this cell, I want to take the action of going right. That's one element of the policy. And you can continue this logic. If I land here, I want to go right. And you can continue the logic as follows. And this is one policy of that you could try to learn using reinforcement learning. I did want to mention, though, that this is not the only available policy. So let's imagine that this negative error goes away, that the reward at this state is 0. In that case, you'd want this component of the policy to actually go up, because you would, if you started here or here, you would get to the reward faster if you didn't go around this obstacle, right? So if this negative reward goes away, you'll want to take the shortest route instead of this roundabout way around the obstacle.
Why does the presence of the punishment matter? Seems like if you win it there, you still
Oh, yes. Touche.
Are you sure you don't mean that you should go directly up in the bottom corner instead if the -10 wasn't there? Because you always want to take the shortest path regardless, and it never makes sense to actually go around the box.
That's actually, well, okay. What you're saying is correct. What both of you are saying is correct.
So you have some chance of going the wrong way.
Exactly. If the transition model was 100% to go the right way, then you guys are correct. But given that there's some noise, there is some reason to go around the obstacle.
Thank you for clarifying.
Yeah, totally. Similarly, if this negative reward was much greater, so imagine that you crank it up to -1,000, you can even conceive of situations where the optimal policy in this state here is to go left. Because 80% of the time you won't move, but 10% of the time you will escape to a safe location, if that makes sense. All right. Cool. So yeah, that's a policy. There are many possible policies that you might want to learn.
So do you want to maximize some sort of expected value of?
Oh yeah, we'll get there when we talk about value functions. Yeah.
Okay.
Yeah, this is just talking about what a policy is, not necessarily how you want to learn it. Yeah. All right, cool. So another way that MDPs are different than Markov chains is Markov chains only have one model of reality, whereas MDPs are agentic. They admit that decision making can alter reality. So let's see what that means. So given that we have this stochastic transition model, let's imagine we have this policy here. This policy yields the following Markov chain. I'll leave it to you guys to verify for yourselves. No, that's actually completely wrong. Oh, no, it's right. Okay. So to verify for yourselves, so what you want to do is you take this kind of purple stuff, the transition model, and in state A, you kind of imagine rotating it clockwise by 90 degrees. And that means that this 80% arrow goes from A to B. And the two 20s, so this 10 and this 10, if either of those execute, A circles back on itself. So yeah, that's one way to think about it. Okay, but if you have a different policy, say this policy, it yields a different Markov chain. And if you have another policy, that yields another Markov chain. So this is just saying that we're not in Markov chain land anymore. Our choice of actions, our policy, will dictate what Markov chain we arrive at. All right. Sorry, I missed that.
The second one,
In the middle, or which row?
row 2A.
For all the probabilities for state A.
Oh yeah.
Same thing with C.
Oh yeah, that's right. Okay, thank you.
Don't worry about it.
Yeah. No, it's okay. Yeah, I appreciate it. I'll update it. So thank you. Okay, so that's Markov chains and MDPs. Now I'm going to talk about reinforcement learning, but I'm going to kind of wave my hands a little bit more on this section because the mathematics is more complicated, and I want to get at kind of the applications before we leave. So to review, let's talk about MDPs again. So in MDPs, for a given environment, a mouse, for example, will learn a policy, this policy here, and then it will execute it. So it will move towards the cheese, if you will. But how does a mouse actually learn the policy? So to learn a policy, what you need to do is you need to compute a reward gradient or a value function. So you'll want to compute this kind of gradient towards the cheese, if you will. And then after you have a reward gradient, you'll want to argmax to discover the actions at each state. Okay, so let me know if that makes sense.
What argmax?
Oh yeah, so let's see. Argmax means that you take the maximum action, the action that results in the maximum value. Okay.
So the action which results in the maximum expected value, right?
Yes, yeah. We'll get there, hopefully. All right, yeah, so that's the philosophy, is we want to compute the gradient and then argmax over it. So let's see. Okay, so let's express this a little bit more formally. So we have kind of an MDP with the following 5 states, 2 actions, transition function that looks like this, reward that at state 5 only you get a reward and a discount probability. So what we want to actually learn is something called a Q state. This is called Q learning, where you have a value associated with every state action pair. So what this is saying is that these 2 boxes on the left are saying that if you're in this first box here, I'm going to associate a small reward by moving right and no reward at all for moving left. Similarly, I'm never going to associate any reward with moving left. Moving left never makes sense. Whereas when I'm moving right, I'm going to associate that action with increasing probability as my location shifts to the right. So what we actually want to learn when we encounter situations like this is kind of this Q matrix, if you will. All right. And then once we have this Q matrix, and I'll talk a little bit about how to learn this thing, but once we have it, then we can say, I'm going to choose which row. I'm going to choose my row based on which cell is greater. So on this leftmost column, the right action has a greater reward. So I'm going to choose that action, right, and put that in my policy. So this is how I'm going to compute my policy. Is I have Q states that I've learned, I'm argmaxing over it. And then I also need to learn a value function, and that's a more straightforward maximum. So I'm going to take the maximum action here. So once I have Q states, I can derive my policy and my value function. Okay. I'm kicking myself for running out of time. That's okay. Okay, so this is the one slide that I have that will answer start to answer David's questions. The real answer is going to be much more complicated. All right, so recall that when we were talking about gradient descent, we talked about designing a cost function that grades the prediction model performance. So we talked a lot about how the larger your error bars are, the larger your residuals, the greater J is. Right. Okay. In reinforcement learning, we're going to learn a value function that grades the policy result. So in machine learning, we learn our parameters by minimizing the cost function. Similarly, in reinforcement learning, we're going to learn our action policy by maximizing the value function. There's a typo. Okay. So one possible way of defining your value function is to say it's the expected future reward. So it's going to be the sum of my reward today, my reward tomorrow, my reward the next day to infinity. So that's one way to approach the value function. But this is buggy. So this particular value function is agnostic to when we get the reward. So it's just as happy with getting water in 5 seconds as it is getting water in 5 years.
Sorry,
of course.
Why doesn't it factor in like time as part of the value function itself?
Oh yeah, so this is we need to bug fix it. It needs to do that. Yeah, this is oh, it's all right. Yeah. Oh no, it's totally fine. It's good to see anticipating great ideas, I guess. Any other questions before I move on? All right, cool. Okay, so yeah, we actually do want to care about time. So what we're going to do is, just as we talked about in the exponentially weighted average section, this is the exact same math. We need to discount tomorrow's reward by some factor, and as we move forward in time, we discount these rewards increasingly much. And this is how we build in a preference to get rewards sooner. Okay, and there's evidence that our brain does something like this. In this temporal discounting, I'll show, I possess biological evidence of it if you ask me for it, but this this neuroscience of temporal discounting explains why human markets have interest rates. We have this kind of value function built into our brains, is what I'm going to claim here. Okay, I'm going to skip the slide even though it's really fun. You can read it in the link that I'll send out. Okay. Okay, so I'm going to talk about deep reinforcement learning, and I'll confess that this is my only slide on deep reinforcement learning, and that's mostly because I don't know as much as I'd like to about the topic yet. That said, hopefully this slide will prove interesting, I suppose. Okay, so most reinforcement learning applications in practice take in raw data as the state vector. So, for example, you see RL engines playing Atari, and they accept as their input all of the pixels kind of condensed into a single vector. But the problem with taking raw data as your state is, as mentioned 30 minutes ago, it's an intractably large search space. So convnets are known for being able to extract abstract features from pixels. So one of the ideas of deep reinforcement learning is, instead of passing in your pixels, why don't you pass in the output layer of your convnet model to your reinforcement learning algorithm? Okay, but I also talked about how convnets have a bug where they throw away spatial information. So what you'd really want to do is, if you're wanting to design a really good deep reinforcement learning algorithm, you'd want to pass in a state vector that contains not just object information, not just features, but also location information, the intersection of the two. So that's the idea of deep reinforcement learning, is people discovered, hey, instead of passing in pixels, let's pass in the outputs of convnets. All right. Oh yeah, okay, so this is another slide relevant to deep reinforcement learning. So reinforcement learning is actually one of the, it has a lot of hype associated with it because it is perceived rightly, in my view, as the future of ML. That said, reinforcement learning just doesn't work well in practice. So almost all robotics, Angel, correct me if I'm wrong, but almost all robotics in practice, for example, Boston Dynamics, they use something called adaptive control instead of reinforcement learning. Why? So reinforcement learning makes a point of assuming nothing about the reward and transition functions. It starts with no knowledge and it kind of builds up its information from scratch. The problem with assuming nothing, with being maximally flexible, is that you're essentially throwing out everything that we've learned in physics. So we could build models that know about Newtonian force, but reinforcement learning intentionally throws that out. And that's one of the reasons why reinforcement learning is so slow and so data hungry. Further, there's a case to be made for maybe it seems likely that our brains aren't doing pure reinforcement learning, that our brains actually know something about physics. So it turns out that 2/3 of your genome is actually involved in constructing your brain. And your genome contains enough information to be able to have your brains immediately know, without any experience, your brains know that snakes are to be avoided. So by the same logic, it's easy to see how your genome could also help the brain anticipate physical reality. So maybe we need to extend reinforcement learning to accommodate prior knowledge, given that biologically we seem to not need to learn everything about physics from infancy. And perhaps the Markov assumption is a little too limiting. We'll talk about this more next week.